professor, drafted your promotion, and vice chair for diversity, equity, and inclusion in the Department of Earth System Science.
I'm not that either anymore.
Also relevant, stretch that, but a full professor at the Earth System Science Department at the University of California in Irvine. Kathleen's research focuses on generating multi-proxy speleothem records from California, Northeast Mexico, and Southeast Asia. Kathleen was an expert back in 2019 in Romania and also during Mini S4. So thank you for returning.
Yeah.
Away.
Thanks for the introduction. Are my slides gonna? Good. That's pretty crucial. Yeah.
I don't know where they went.
Is the PDF?
I opened it earlier, but we can. Let's see. Maybe this?
Uh-oh.
False alarm. No. Oh, that is it.
Yeah.
I couldn't figure out how to make it like full screen.
Three dots on the right. Yeah.
Tenta colocar o L.
No.
Yesterday was definitely there. Or just press it.
Três pontinhos lá em cima.
Either one. I think I just sent one, so I think they're the same.
I think the slides advance as is. It just has the little border around it. If we're okay with that.
But it's the same computer.
But it should be able to do a slideshow.
Yeah, it's in the slideshow.
Ctrl L.
F5.
No?
Visualizar.
Some famous scientific high level of business. We are not managing to get in a big screen. Nice.
All right.
Hooray.
All right. Thank you, Elizabeth, for the introduction.
I'll give you these.
Okay, awesome. Thank you for the introduction. Yeah, I'm really excited to be back at S4 again, so thanks so much to all the organizers and hosts. This is my first time in Brazil and first time in South America, so very exciting. So yeah, I was asked to talk about trace elements and speleothems, which is a subject I am very interested in because I think trace elements are a vital part, or should be a vital part, of every paleoclimate study. That said, they're not without complications and they may not always work, but I think investigating them and their potential with every record is something that I would highly recommend because you can get much richer information about past climate, in particular about past hydroclimate. And so I'm gonna give kind of an overview. This is a really big topic for a 1 hour lecture. And I also wanna acknowledge some folks who I borrowed some slides from, especially Andrea Borsato, who you'll be hearing from next. Okay, so I'm going to start by giving an overview of where trace elements are coming from when you measure them in your stalagmite or in the drip water in a cave, as well as how they are transported into the cave and incorporated in speleothem calcite. And then I'm going to focus on reconstructing hydroclimate with trace elements, mainly by focusing on the use of prior calcite precipitation signals or incongruent calcite dissolution signals, which are very closely related, as you will see. And then, depending on how much time, I've got several case studies with some examples that I can show from some of my work and the work of others. And then I'll end with some practical considerations for those of you who might be thinking about measuring trace elements in your samples. So this figure is modified from an older figure from Ian Fairchild's review paper in 2006, and it was from the elements issue that Hubert mentioned earlier. And basically this is showing a summary of all of the different parts of the Earth system that can potentially influence the geochemical signal that we're measuring in the stalagmite. And Fairchild et al. Kind of categorize these into these 5 main categories: atmospheric inputs, which could be from anthropogenic sources or from volcanic sources or from other types of aerosols and dust. Vegetation and soil inputs, inputs from the karstic aquifer or the bedrock, which, as well as signals that are related to the crystallization of calcite itself, so primary speleothem growth. And then there's potential for secondary alteration, but I won't focus on that too much because as we know, thankfully speleothems are pretty protected from alteration in many cases. And then a lot of what I'm going to talk about as well, it was covered in this other later review paper from Ian Fairchild and Pauline Treble in 2009, which I recommend you all read. Okay, so with regards to the sources of these elements, like I said, they can be coming from the atmosphere by wet or dry deposition onto the land surface, and then that can be leached down into the cave along with the drip water. You can have sources related to vegetation growth and dieback of the vegetation, especially things that are related to nutrients like phosphorus or maybe sulfur can be related to that. And then you can have elements that are in the bedrock, whether that's in the limestone itself or dolomite itself, or whether it is in accessory minerals that might be in there, like pyrite, for example, or apatite could potentially be a source for phosphorus. And then, so you have organic matter decomposition, dissolution of carbonates and other minerals. You can also have material transported as colloids, which I'll talk a little bit about. And then you can have mixing between waters with different flow paths that can complicate matters. And then this mechanism of prior calcite precipitation that we've already heard a little bit about in other lectures and that you're probably all familiar with is one of the most widely applied interpretations when we're talking about using trace element records for past hydroclimate. Okay, so what elements in particular are we talking about here? So this is again showing those different sources with several of the different atmospheric sources shown over here. So things like chlorine and sodium, as well as magnesium, strontium, sulfur might come from sea spray. Other elements like sulfur and molybdenum could also come from volcanic sources. Aeolian dust often has a lot of strontium in it. And then anthropogenic signals like sulfur or lead. So that's one potential input into the cave system. From the soil and vegetation processes, we might see phosphorus or silicon, also these sort of refractory elements that might be transported as particulates, things like lead or iron. In the bedrock itself, of course, that's where we get the majority of our calcium, but it's also typically where we get the majority of magnesium and strontium, although I will note that both of magnesium and strontium can also have other sources, for example, aerosols. And also, bedrock itself can be somewhat variable. So younger bedrocks tend to be more heterogeneous in their chemistry, whereas older bedrocks tend to be a little bit more homogeneous. So actually understanding and sampling the bedrock at the cave site that you're working in and measuring the elements in it can be really helpful and is a good idea. And then within the cave itself, you can have other sources of trace elements to your samples. And that can be things like guano, but also aerosols within a cave and flood deposits. So those are all the things that, this is by no means an exhaustive list, and there are definitely other elements that might be interesting. Okay, so just to show a few examples of some of these different sources. This is from Tremaine et al. 2016, and these graphs on the left are showing different elements versus chlorine concentration in drip water samples from a cave in the South Pacific. And chlorine is assumed to come entirely from sea salt, and so that can be used as a conservative tracer of sea spray in this particular case. And so when we have all of the drip water data plotting on or above this line that is the seawater line here, that's showing that that can be used to determine how much of that particular element came from sea spray versus how much might be from other sources, and or enriched through processes like prior calcite precipitation and other transport-related processes. So in this setting, which is a really coastal cave, you can see that sea spray is the main source of chlorine, sodium, magnesium, sulfate, and potassium, as well as a significant source of strontium and calcium and other elements. Strontium is also delivered from other aeolian sources. Dust, as I mentioned, is a potential source, and this is showing, this is again a record from Sorek Cave in Israel, showing the oxygen isotope composition compared with strontium concentrations and also strontium isotopes. Strontium isotopes are a really useful tracer for sources of strontium. It can help you distinguish between sea salt sources, dust, soil, bedrock, as long as you have different isotope compositions and can characterize those reasonably well. And so this record here was interpreted as showing elevated levels of sea spray and dust reaching the cave site during the drier conditions of the last glacial, and a shift towards a more host rock dominated signal, which was interpreted as wetter conditions during the deglacial and Holocene. On the right here is a more recent study from Belli et al. In 2017, which is, in this case, they also used strontium isotopes to distinguish between different sources. But in this case, they actually took it a step further and corrected the strontium data by removing, using the isotopes to correct for this exogenic strontium and backing out what strontium was delivered from the host rock itself. Uh-oh. There we go. Okay, so that's kind of just a quick summary of some of the aeolian sources that can be measured and recorded in stalagmites potentially. Another important point, though, is that it's very important to think about the ways that these elements are actually getting into the cave. So, and this was this figure here from Fairchild and Treble's review paper kind of categorizes these into three different types of sources and modes of transport for trace elements into the cave. It can be as particles, and that can include things like silica, iron, titanium, aluminum. It can be as solutes, which are the dissolved ions that we think about, like calcium, magnesium, strontium, often these alkaline earth metals. And then in an intermediate size fraction, we have between about a nanometer and a micron, we have these sort of colloidal forms of material that can be transported. And these often are associated, can be inorganic or organic, and include things like humic substances, some silicates, as well as oxides and other things. And these can be strongly associated with particular elements. So this figure, which I stole from Andrea, is showing some different elements that might be commonly measured along with kind of their dominant mode of transport. So things like barium, calcium, sodium, magnesium are in dissolved form when they're transported into the cave, but other things like phosphorus and sulfur, bromine, uranium might be transported as solutes, intermediate solutes or colloids, and these sort of more refractory titanium, manganese type elements are often transported as particles. So understanding how these elements are getting into the cave is really important, because if something is transported as colloids or particulates, it might have the completely opposite environmental interpretation than if it's transported in a dissolved form. So this is where cave monitoring can be really helpful and critical, really. Detrital elements, as I mentioned, have potential for use as paleo flood proxies. This is a review paper by Dennison and Lucher, showing these aluminum-rich layers associated with known flooding events in this cave system here. And that's something that is a really exciting potential research area, although also really challenging in part because, as those of you who have worked on uranium thorium dating know, we generally want to avoid samples that have a lot of detrital material, and it can be really hard to date them. So that's one of the challenges. The hydrology of the specific cave that you're working in also can have an impact on the transport of different elements in different forms, with like a filtering effect. So this is another figure from the Belli et al. Paper, and in this figure, this is showing some elements which are more detrital, detritally transported, and solute transported, so magnesium and strontium down here, thorium, aluminum, manganese up here. And this is comparing two different stalagmites that formed over the deglacial period. And one of these stalagmites is characterized by really diffuse matrix flow, and another one is more characterized by a mixture potentially of fracture flow and matrix flow, the black records here. And so you can see that just the different hydrology of these two drip sites can lead to different signals, where during these gray bars are highlighting thorium-rich layers. And you can see that the fissure flow shows much bigger responses in the detrital elements. During these periods of rapid infiltration, you can have much more transport of things like aluminum, manganese, and thorium through flow paths that are more fracture dominated than those that are more matrix dominated. Whereas down here in the solute phase, you can see the two stalagmites look a little bit more similar, although you can also see some instances where there is likely particulate or detrital transport of magnesium and strontium as well. So one way that I think is a really useful way to actually analyze the data was demonstrated in this Faraji et al. Paper in 2021. This is showing some micro-XRF and LA ICP-MS data for several elements down here below here. And to try and understand how these different elements were covariant with one another, they conducted principal components analysis, and the loadings for this PCA is shown over here on the right. So basically things that are clustering together on this plot likely share a lot of variance and likely are reflecting a common source or process. And so in this paper, magnesium and sodium, which have this negative loading over here, were interpreted as primarily related to aerosol deposition from marine aerosols, whereas strontium and barium over here are interpreted as primarily coming from the host rock, and then phosphorus and yttrium, which are pretty similar but a little bit separated potentially, are likely more soil derived. So you can do this to try and interpret different elements robustly, and using this kind of multi-proxy approach. When you see these clustering effects, you can be more confident that, for example, these soil-derived elements might be enriched during periods of wetter conditions and higher infiltration, and that can help with your interpretation. Okay, so with that summary, I want to kind of shift a little bit and focus on the incorporation of elements in the calcite itself. So these detrital and colloidal materials can typically be incorporated as discrete particles or on defect sites in the calcite, adsorbed onto the calcite, not necessarily part of the crystal lattice. But when we're talking about magnesium and strontium, often, and potentially barium, we're often talking about thermodynamic partitioning of these elements that are actually substituting for calcium within the crystal structures of calcite or aragonite. So this concept of partition coefficients or distribution coefficients, which are often summarized called D or sometimes KD, this distribution coefficient basically is a very simple mathematical formula where X over calcium in the calcite divided by, is equal to, the distribution coefficient D is equal to X over calcium in the calcite divided by X over calcium in the solution, where X is the trace element of interest. These are molar ratios, important to say. And so if you have a highly compatible element, for example, cadmium is one element that has a very high distribution coefficient, it'll actually preferentially go into the calcite. But many of these elements that we're going to be talking about, magnesium, strontium, and barium, have a much lower, have a D much less than 1. And so that is telling us that they prefer to stay in the solution phase. So when calcite precipitates, those elements are preferentially excluded, whereas calcium is taken up. And so changing the amount of calcite that's precipitated will then therefore change the solution, the X over calcium ratios in the Romanian solution, and hence in any stalagmite that subsequently forms from that. So these distribution coefficients are typically, even though they're kind of thermodynamic coefficients that should reflect some sort of equilibrium precipitation, they are actually primarily determined empirically, and that has been done through, well, in the classical mineralogy literature, there is like a very rich literature on trace element partitioning, but it has been shown that somehow caves and cave systems might behave somewhat differently than sort of inorganic carbonates or biogenic carbonates like forams. And so the appropriate D values to use are likely those that are based on lab experiments that were conducted under cave analog conditions, or that are based on actually measuring natural samples in the field. So you can go out to your cave, measure the ratios in glass plate modern calcites and in the drip waters, and calculate site-specific distribution coefficients if you have a lot of monitoring data available to you. So these distribution coefficients are interesting because they also show some dependence on environmental parameters, potentially. So temperature, growth rate, water chemistry have all been shown to potentially affect how these elements are partitioned into the calcite. Here's just a subset of some of these key studies. Wong and Fairchild measured a lot of drip waters to look at partitioning of and conducted lab experiments to grow calcite under karst analog conditions, as well as Day and Henderson, who looked at a suite of different elements in order to try and look at the impact of factors like water chemistry, temperature, saturation state, and growth rate on the distribution coefficients themselves. And then there's other studies like Tremaine and Freilich or Wassenberg et al. That actually took samples from natural caves to try and look at distribution coefficients across different types of conditions. So temperature dependence, this is a good follow-on from the earlier talk about paleo temperature records from speleothems, because actually like magnesium calcium measurements of stalagmites was originally the focus, like back in the 70s, was the focus of speleothem research aimed at trying to develop paleo temperature records. The problem that was realized, and that has still not been overcome really, is that the changes of the magnesium calcium of the calcite is not only affected potentially by the distribution coefficient, but also by, which may be temperature dependent, but also by the solution composition. And we know that the magnesium calcium ratio in karst waters can vary quite a lot more than what is typically driven by temperature. So this is showing three of these different calibration studies that did find significant relationships, positive correlations between the D magnesium and temperature. So at higher temperatures, magnesium is more magnesium can be incorporated in calcite. So that's pretty clear. The problem is that the slopes these relationships don't all agree in their magnitude, and that might have something to do with other factors, like where exactly the magnesium is being incorporated. Is it sometimes being incorporated in non-lattice sites? And also, like I said, in the vast majority of cave settings, changes in the magnesium calcium of the drip water is going to be much bigger than any temperature-driven signal. So not so much useful for a temperature proxy. Similarly, there's been in the past a big focus on whether strontium calcium variations might be useful for reconstructing changes in growth rate of the speleothem. And this has really mixed results. It seems to, so Wang and Fairchild found a significant relationship in their lab studies between D-strontium and growth rate, with faster growth rates favoring more incorporation of strontium in the calcite. Day and Henderson, however, did not. And then also this recent study by Wassenberg et al. Also did not find a significant relationship. But then this Belli et al. Study did find what seems to be a convincing relationship between strontium concentration and growth rate. And so as far as this goes, there's still no consensus really. So I guess proceed with caution. Some of this uncertainty in the strontium might be due to, and also maybe in some of the other distribution coefficients, might be due to things like what are shown here, Drysdale et al. In 2019. This is showing a plot of D-strontium versus sodium-strontium ratio. And they found a significant relationship or dependence of D-strontium on the sodium concentration in the drip waters. And that was, this wasn't drip waters, this is a subaqueous calcite. But in this case, they found that sodium might maybe outcompetes strontium in some cases for non-lattice sites, so that the higher amount of sodium you have in the drip waters, the less space there might be for the strontium, and hence this relationship. Over here on the right, this paper by Wassenberg et al. In 2020 found similarly that the distribution coefficient of strontium also is correlated with the magnesium calcium of the calcite. And this was attributed potentially to the fact that the size of the magnesium ion is much smaller than strontium. And so when and this has been previously hypothesized as well, that if you substitute magnesium for calcium in the crystal lattice, that basically makes more space in the crystal structure, and so that the strontium can then fit in better in other places. So it's this kind of warping of the crystal structure that might happen. But they also speculate about this potentially being linked to crystallization pathway effects, whereby there's this amorphous calcium carbonate precursor that affects the incorporation. Okay, so this is another figure that I think Andrea compiled that is a summary of some of these different distribution coefficients. So in addition to the ones that I talked about, this is showing uranium and sodium as well. So you can calculate and determine distribution coefficients for other elements, but it's not always clear whether those are appropriate to use or not. But as you can see, there's many different, each of these has a given range that has been identified in the literature so far. And there are potentially environmental controlling factors and other complicating factors that should be considered if you're going to be measuring and interpreting any of these elements in your stalagmite samples. Another factor that should be determined, and I'm just going to brush through this really quickly because Andrea is here and I don't really want to talk about fabrics in front of him. And you will hear about this coming soon. And so, but it is clear that there are relationships between the types of calcite fabrics and the incorporation of specific elements. And whether that's a chicken and an egg situation sometimes is not clear to me. I'm sure Andrea could talk more about that. But in any case, this is showing an example from Frisia et al. In 2012, which was looking at this really old 4 million-year-old stalagmite from the Nullarbor in Australia that has these kind of micritic stromatolite-like layers, which are enriched in several trace elements compared with more kind of parts of the same samples that are more columnar fabric, and also enriched relative to the bedrock. So things like phosphorus, manganese, aluminum, and iron seem to have a clear link with these layers. There's also a lot of evidence for sectoral zoning in stalagmites. So this is showing, it's hard to see the different elements here, but this is ICP-MS raster scanning from Slowinski and Stoll 2021. And you can see like annual lamina in several of these elements, things like strontium, which often has really good annual lamina. But if you kind of look at these kind of cross-cutting features in some of these elements like magnesium, nickel, and sodium, you can see that there are other types of zoning that can impact the sample. So this is one example of why, if you're doing like laser ablation ICP-MS, it would behoove you to do multiple scans so that you average out some of these spatial patterns. Also, the particulate forms of material that can be incorporated in stalagmites can lead to really discrete peaks in different elements. So here you can see some particulate inclusions that are rich in strontium from this Cook Island stalagmite from Borsato et al. 2021. And these particulate inclusions are corresponding with porous layers in the calcite. So more open columnar or porous fabrics, which might be a reflection of a wet event where you have a high infiltration bringing particulates into the cave. Okay. So from here on out, I'm going to focus mainly on trace element variations that are linked to distribution coefficients and incorporation at crystal lattice sites of magnesium and strontium or barium. And so just as a reminder, I think everyone knows what PCP is. Pericalcite precipitation, governed by this distribution coefficient, is effectively, if you have, this is obviously a very simplified picture here, where you have water moving through the karst, and calcite being precipitated when you have CO2 degassing happening anywhere in the epikarst. This can also happen on the cave ceiling in the form of stalactites. And the calcite preferentially excludes these incompatible elements. And so because of that, it's removing calcium, but not removing as much magnesium or strontium. So you have an increased X over calcium in the remaining drip water. So the more PCP you have, the higher the X over calcium gets. And kind of the dominant paradigm is that drier conditions, when you have less saturated conditions in the epikarst, in the soil, and maybe slower infiltration, should be associated with more PCP and therefore higher ratios of magnesium, calcium, strontium, calcium, etc. There also can be effects from within the cave that can be driven by things like changes in drip rate because the extent of calcite precipitation and degassing on the stalagmite surface can actually change depending on the drip interval and lead to changes in the trace element concentration. You can also have changes driven by PCO2 in the cave. So when you have higher PCO2 in the cave, the degassing happens more slowly, and therefore you might have less PCP. So it's important to know, and that's just a bit of an aside, important to understand the ventilation patterns in the caves that you're working in and whether there's seasonal ventilation or not. That can change the PCO2 in the cave air and induce some of these trace element variations. So PCP has been shown and demonstrated to be a thing that does happen in many different cave sites, but not everyone. And often there can be really confusing situations where you might have magnesium and strontium closely correlated for periods of time, and then anti-correlated for other periods of time, etc. And so there are ways to tease apart and verify what's happening, but a lot of times it'll either require a multi-proxy approach and a lot of cave monitoring. Okay, so if you want to diagnose whether PCP is happening, this is one approach that was proposed by Fairchild et al. In 2000, and this is just plotting calcium concentration versus magnesium calcium concentration. So if PCP is happening, you would expect that the more calcium that's removed from solution during this PCP, the higher the magnesium calcium should get. So these are sort of modeled lines versus data showing this effect. So that's one thing you can potentially do if you have different drips that you can measure, for example, over long periods of time. And ideally, it's not always possible. So for younger samples where this is an active sample and you can measure the exact drip, that's really the best. But sometimes that's not possible. In fact, a lot of the caves that we've worked in, it's not possible. So measuring other drips in the cave can also be helpful potentially. And then the more classic way, or the more common way, sorry, that's cut off a little bit. This should say Sinclair 2012. So the more common way to kind of try and diagnose PCP is by looking for this characteristic correlation between magnesium, calcium, and strontium calcium. So Sinclair and others showed that PCP should result in a linear slope in log-log space of strontium calcium versus magnesium calcium with a slope of around 0.88. And the reason for this, they prove mathematically, is that this slope should should equal the d strontium minus 1 divided by the d magnesium minus 1, okay? So you can plot magnesium calcium, strontium calcium against each other, either for your drip water data or for the calcite data, and see that there is a correlation of 0.88, boom, PCP, you can interpret your data. That's, however, not entirely the case, because as was also pointed out by Sinclair et al. In 2011, another process called incongruent calcite dissolution can lead to that same slope. You'll also see that there's a range in slopes here, and this was based on at the time, all the published values of d strontium and d magnesium. But they determined this 0.88 was the best. Okay, so what is ICD, or incongruent calcite dissolution? Sometimes this is just lumped together as like water-rock interaction. So congruent dissolution is, I think, helpful to understand first before thinking about incongruent dissolution. So congruent dissolution is just simply that when you dissolve the bedrock, the trace element ratios in the water are exactly the same as they were in the bedrock. So that's what we would hope would be the case. But in reality, incongruent dissolution is a process that happens widely. So in incongruent dissolution, the trace elements are released from the bedrock with a ratio that's different from the host rock, or from the bulk limestone. This is the size of this is hard to see, but this is the natural log strontium calcium versus natural log magnesium calcium for some limestones, as well as the leachates from those rocks, showing that the leachate was always a higher concentration, higher magnesium and strontium concentration than the bedrock itself. So this was showing one type of model where there's preferential leaching of magnesium or strontium from the limestone. And that's actually, in Sinclair et al., that's kind of model number 2. And that's kind of the easiest to understand, I think, where maybe those are sitting in sites that are just the bonds are more easily broken, whatever. The other model for ICD is a little bit more complicated, and it involves basically dissolution of the limestone that's basically simultaneously almost occurring with calcite reprecipitation. And so in this model, you have this bulk calcite, and you're dissolving it, and the dissolution itself may initially be congruent. But then you have this reprecipitation, and the magnesium-calcium ratios in the reprecipitated calcite now are going to be set by the solution composition as well as that distribution coefficient. So you're going to effectively have a PCP-like signal that happens. The more of this that occurs, you're going to increase the magnesium-calcium and the strontium-calcium in the remaining solution. This in this particular 2011 paper, it's argued that this model 1 is most likely the one that is, This model 1 is most likely the one that is dominant in most car settings and able to cause bigger changes, and that's effectively because this preferential leaching effect only can go a little bit far, and then like the longer dissolution proceeds, the more congruent it becomes effectively. Okay, so there are some other complications, so things like temperature and changing, so all of that assumes that the distribution coefficients are constant, but as we have already talked about, they can vary over time. And so the Day and Henderson experiments, they found this temperature dependence of D-magnesium, and so they were calculating the effect of prior calcite precipitation, which is in this case modeled as a Rayleigh fractionation type process, where you're progressively removing calcium from solution and enriching the remaining magnesium calcium dependent on the distribution coefficients, and then they incorporated changing temperature in here. And so this is showing temperature versus F, or the fraction of calcite removed, so basically PCP is proceeding to the right here. And so if temperature was the main effect, you would expect these contours to be pretty much vertical, but they're not here for magnesium calcium. And so they basically conclude that changes in solution composition are likely more important than temperature. Another really interesting finding is that from Day and Henderson over here is that mixing, they basically showed that if you, so we talked about mixing, somebody talked about mixing lines yesterday. That was JP, I believe. So mixing lines can also affect or confound the trace element ratios that you're measuring. So if you have solutions that have different flow paths and different amounts of PCP, so this is showing kind of a PCP curve, this bottom curve here, for the distribution coefficient versus F. You can have these different, end up with these different compositions that have different Fs, and then if you mix them together, you can create a wide range of trace element signals. On the right here is another figure from Wassenberg et al. In 2020, where they basically, based on that relationship they found between the magnesium-calcium content of the calcite and the distribution coefficient for strontium, they found that basically changes in the distribution coefficient could actually mean that actually slopes that previously were rejected as too steep for PCP may actually be explained by PCP if you have a varying distribution coefficient within the range that they found. So other things to keep in mind. So the slope itself is helpful to diagnose whether it's PCP/ICD happening. There are ways you can try and distinguish between those through monitoring data, potentially. But I'd say just because you have a slope that falls outside those Tremaine et al. Bounds doesn't necessarily mean that it's not happening. Okay, so I've made it to the case study part. I'm going to have to skip over some of these. This is a study that I published way back in 2006 that was showing annual seasonal variations in a number of trace elements and stable isotopes. And we modeled magnesium calcium as a Rayleigh fractionation process, along with delta C13 using Freak-C to show that these seasonal variations were likely being driven by PCP. And so if you plot, one other way to potentially identify PCP is if you see covariation between magnesium, calcium, and C13, that can sometimes be evidence because as that PCP is proceeding and you're degassing, you're preferentially losing the carbon-12. And so you might expect this sort of correlation, which is what we found here in this Hishan Cave stalagmite. As a bit of an aside, another application for trace element measurements, this is a micro XRF, synchrotron micro XRF map of strontium that Andrea collected from a stalagmite that we were working on from Tandunmai, Laos. And we found annual lamina in strontium that were very fine. The growth rate of the sample was around 20 microns per year. So it was hard to see in without any other tool. And we were able to use this XRF data to actually count lamina and create a floating layer counted age model, which we were then able to anchor to the uranium thorium age model in order to get this very kind of decadal resolution record over the common era. This is showing a couple of early examples from Treble et al. And McDonald et al., which showed basically that there are monitoring data or additional proxies that confirmed this interpretation where PCP was increased during drier periods. A very famous example from Bachivera Cave, which you may have already seen. I missed Chico's talk yesterday, so maybe you've seen this already. But this is this amazing kind of orbital scale variations in magnesium, calcium, strontium, calcium, which provided really strong evidence for orbital scale hydroclimate variability in the South American monsoon region. And this is another example of a really interesting way that trace elements can complement our interpretations of paleoclimate by providing more specific information about local rainfall. And this is especially important, I think, in areas where the interpretation of the oxygen isotope signal is unclear, or maybe isn't, like the Asian monsoon region, we know that it's this large-scale signal that isn't necessarily directly related to rainfall amount at a specific location, but we can look at things like carbon or trace elements, which are driven primarily by local processes to distinguish that. And so this study was quite surprising in that it found that Heinrich Stadial 1, which is widely seen as this weak monsoon period in China, actually was wetter in the central Yangtze Valley region, and that was linked to changes in the seasonal transitions of the westerly jet. And then one last case study I'll talk about, which was just published by Elizabeth Patterson et al. In PNAS. So this is her. This is an amazing, nearly 4 meter long stalagmite that we collected. It was previously broken in several pieces. We managed to find them all and piece them all together to create this continuous sample. And this happened in March 2020. So we got back to the US like just a day or two before everything shut down for COVID. And so Elizabeth took this sample home with her. This is her in her apartment in her pajamas, where she faithfully polished this while watching Tiger King. Yeah. So 2020 throwback. And so anyway, we just published this really cool record which shows this remarkable similarity between magnesium, carbon, and actually oxygen isotopes as well. But also we have other evidence like uranium-234, 238 initial ratios, which support this interpretation where the higher values are interpreted as much wetter conditions. We also have faster growth rates during some of these periods. And this was linked in the study to, well, orbital and millennial scale changes definitely affect the record, but the really dominant signal is explaining some of these really abrupt transitions is that sea level, when it rose, flooded the continental shelf upstream of our region and cause much wetter conditions. Another interesting thing from this, you can see that kind of you reach this potential kind of plateau in magnesium calcium, where it does suggest that there is an upper limit to the sensitivity of this proxy. So that might be a situation where it's so wet that there's no PCP happening, and beyond that we can no longer interpret the record. So there'll be some other forthcoming papers related to this using some other proxies. Okay, I will stop there. I'll skip over the Griffiths one, but that's just another example of a record that we have from Laos. Just let me say at the end a couple of take-home points. I was going to have several slides on this, but I ran out of time, so it's good that I only have one. So basically, cave monitoring is really important, and it's not possible, like as somebody who works in caves that are located far away from where we're living, it's really hard to do reliable cave monitoring without really, strong support from local collaborators, which I always encourage. But even a little bit of cave monitoring can go a really long way. So if you're able to get some basic measurements of drip water chemistry, ideally in at least a couple of seasons, measure the bedrock composition, measure some of the cave environmental parameters, at least like at a couple of different times of the year, like CO2, drip rate, temperature, humidity, etc. That can provide a lot of context to your interpretation. When you're thinking about what elements and isotopes to measure, that's a pretty big question. So magnesium and strontium are the most widely used, and I think that's because we do understand them pretty well. And have shown that they can be useful, but don't overlook other elements, especially if you're doing like laser ablation data or solution ICP-MS data where you can measure a lot of elements. Measure everything you can that you have the sample for, because those detrital and colloidally transported elements can provide information about infiltration rates, soil vegetation, etc., and also provide further support to PCP interpretations. So multi-proxy approach, strongly encouraged. Analytical methods. There is a huge range of these, and for this I would point you towards, we can actually put this in the WhatsApp or something later, but the CISL lectures that Andrea gave last year, I think, or was it this year? I don't know. One of these recent years, which go into much more detail about the different analytical methods that you can use for measuring trace elements. There's a lot of factors you have to balance, including the speed, the cost, the access you have to it. Like, it's not everybody can go get synchrotron time, as well as considering how much of your sample you need to use up and whether you need to section it into a bunch of pieces. For example, a 4-meter stalagmite, it's not feasible really to do like laser ablation on, so we did all those measurements by solution. And then you can also use geochemical models or things like cave calc, ICEL, simple Raleigh models to improve interpretation of your data. So I'd recommend looking into those. All right, thanks.
Thanks, Kathleen, for a great talk. We do have a few minutes for questions before lunch. Yes.
It's really interesting talk. So I have a couple of questions. My first question is that you talk about the strontium and magnesium to interpret PCP, right? So can we use uranium as well?
Uranium?
Yes.
Potentially, sometimes, but uranium is much more complicated often because I think it often is associated with colloids and transported in that way and not necessarily always incorporated in the calcite lattice.
All right,
So if you see it correlating really strongly with the other elements, that might be a sign that that is a dominant mechanism, but not always the case.
and about partition coefficients, you mentioned that we should measure some ratios between calcite versus solution, right? So for example, if we are measuring trace element composition of a particular layer which maybe formed between like thousands years before, how could we make some relation between the current drip water concentration? How it's possible?
Yeah, that's a good question. So it's hard. So like if you're working on older samples that maybe were formed on, under different hydrologic settings, etc. I think using multiple proxies within the sample itself is probably the best strategy. Cave monitoring is definitely helpful, but you have to assume that the system and the controls have stayed the same, right, over thousands of years.
Yeah. I'm thinking that, for example, how we can know that the drip water concentration is still remains constant through that period of time?
Right. So usually the drip water data isn't remaining constant,
Yeah.
right? That's what's being driven by PCP. One thing even if you can't distinguish between PCP and ICD based on your speleothem data, one thing I think I forgot to mention is that it does seem that ICD also, that type of recrystallization ICD, like water rock interaction, likely does increase with drier conditions as well. So either PCP or ICD, both should lead to higher ratios with drier conditions, even if you can't distinguish exactly which one is happening.
Actually, I was curious to know like how PCB-based records align with the climate models and either the gradient are into the simulation. So
Sorry, how the PCP-based records align with climate models?
I was just curious to know.
Well, I think the last record I showed is a good example. I don't have a plot of it here, but in the paper, in Elizabeth's paper, we find, so we use the iTrace model, which covers the deglacial, and basically showed a really strong correspondence between rainfall in the model and the signals that we're recording in the stalagmite, including the timing of this really abrupt shift around 14,000 years ago. So that was really encouraging. So I think it is possible. We've also used, I didn't show this one. This is this record, Holocene record from Tandumai, Laos, where we closely coupled it with model data to kind of understand the dynamics of what was happening to explain this mega drought that we identified around kind of 3 to 5 Ka in this region, and we used simulations of the Green Sahara basically to argue that the demise of the Green Sahara affected the water circulation in a way that it caused drying across this region. And so the patterns in the model, along with our data, but also other like non-speleothem based proxy records, seemed consistent with that. So I think that's something that I think is really useful.
Okay, one quick question.
We usually focus more on the PCP, understand the parameters like temperature, growth rate, and the water chemistry. What about the PAP, prior aerogenite?
Oh, good question. So I don't know as much about prior aragonite precipitation, but so anyone else could chime in if you do. But because different elements will have different affinities, so aragonite will have much higher concentrations of uranium, for example. So that can prior aragonite precipitation has been linked, I know, to uranium-calcium variations in speleothems.
Can you suggest some research paper based on the PAP?
I will have to look it up, but there's one I'm thinking of. I think it's from Belize or elsewhere in Central America. Anyone know prior aragonite precipitation? I'll look it up. Yeah.
Yeah, with aragonite you have to be very careful. First of all, because the compatibility of the elements is completely different than calcite, but also because it may happen in an environment where first you have prior calcite precipitation, and that might lead to aragonite precipitation. So the signatures are going to be way more complex.
Mm-hmm. Yeah, but there is one paper that I know of, but there's probably more that I'm unaware of, so I can look it up and tell you later.
All right, well, let's thank Kathleen one more time. And then a couple announcements. announcements about lunch. We're gonna do the lunch tickets a little bit differently today. We're gonna have someone stand at this door and hand you a ticket, and then you can walk over to lunch on your own, but please be back by 1:20. And if you don't have a ticket, you won't be able to pay for your lunch. So please exit this way.